What is up, my freaky feathered friends? Welcome, and I just used an alliteration. That's right, 3 or more words that start with the same letter. Alex the alligator ate some apples. Came here for some math, got some English. Boom. Welcome. Let's go ahead and get into the math. So, this is going to be one of 2 topics for the video. The first one is graphing quadratic inequalities, and this in itself isn't a new skill, it's just a combination of 2 skills that we already know, right? Graphing quadratic inequalities is just a combination of graphing quadratics and graphing inequalities. Okay, so we're going to take this skill, and then we're going to do that skill on top of it. Neither of the individual methods change, right? So nothing about our logic changes, nothing contradicts itself, nothing interferes with each other. It's just that we're taking one thing and we're adding another to it, right? And that's okay. That's completely okay. It doesn't change the purpose, it doesn't change the reasoning behind either of those individual things. So we can do this. So let's go ahead and look at these 2 skills individually. To graph quadratics, so our first skill, find the key features such as, and I thought this was a family-friendly YouTube channel. I guess not. Sorry guys, this is going to have to be rated R. I actually don't think you're going to be able to watch this anymore now. We're going to have to set it to above 18. Man, I need to hire a better editor. Who edits these things? You're fired! Dang it, that's me. Okay, such as the vertex, the concavity, and the stretch or compression, right? Such as, right? Right? Not a bad word there, just AS, okay? Pretend we didn't even see that. So, we're looking for the vertex, the concavity, and the stretch/compression. Okay, we're looking for those features because they are key features of a quadratic. They tell us what this quadratic is going to look like, which is exactly what a graph is. A graph is just a visual looking at a function, right? Graphical, right? Something that's graphical we can see. That gives us an image of it, the same with a graph. Okay, so we're going to look for these features and then graph such key features. Right, so skill number 1. Okay, I'm actually just going to write part 1 up here because that is our first skill. Okay, and so keep in mind, right, if this is the part you get stuck at, it doesn't necessarily mean you don't know the second part. And vice versa, if you can do the first part but not the second part, that just may mean you need work on the second part. Right, 2 individual skills here. Now, here are the rules to graphing inequalities. Okay, so just really straightforward. Our second skill. We'll go ahead, write part 2. Part 2. Okay, if the y value is greater than the x value, right, meaning that we have this kind of sign with our y on this side and our x on this side. So it actually, side note, sorry, that was actually a bad misspeak of me. It doesn't matter which side it's on, it just matters which way the sign is opening. This sign is opening towards the y, therefore the y is bigger than the x. Okay? So whenever our y term is bigger than our x term, so this is opening up towards our y term, shade above the y value, aka shade above the line. If the y value is less than the x value, look at this, our sign is facing the other way, it's opening up towards our x, because x is greater than y, we're going to shade below the y value, right? Y is less than x, so we're going to shade below the y value, aka shade below the line. If the inequality has an or equal sign, okay, now look at this. This is the difference between the 2 signs. So here's our 2 possible signs, our greater than and our less than, and our greater than and our less than, but notice these ones have lines under them. Okay, if it has a solid line under it, that means or equals, right? It can be greater than it, or it can actually equal it. Likewise, it can be less than it, or it can equal it. So if it has one of those signs, the graph has a solid line. Now how we can think about this is that when we have a solid line, right, that means we can touch it, that means we can be on it. So not only can we be greater than it, but we can also be equal to it. That's why we draw a solid line. It's okay to be on it. If the inequality does not have an equal sign, right, so just a greater than or less than, no equal sign underneath it, then the graph has a dashed line. Okay, and the idea behind that is we can get really close to it, but we can't quite touch it. It's not a full line, it's a dashed line, because we can get close to that boundary, but we can't quite rest on that boundary. Can't have a point on there. Okay, so now let's go ahead and look at this. So right here, I know it doesn't say anything for the prompt for this question, but if it did, it would say, graph this system of inequalities. Right, and you want to think about that. Why is it a system? Why would we call this a system? We call this a system because it has more than one equation. Right, and that kind of makes sense. A system can't be made up of just one thing. A system implies more than one thing. So here is our system of equations. So this means we're going to have to graph two of these things, right? We're going to take this two-part skill, right, part 1 and part 2, and do it twice to this. Okay, and that's actually going to be our whole example, and I can even annotate each part of it, just so that way you can go to each part, right, and really break this up. Because understand, this is a massive problem, right? We have a two-part skill repeated 2 times. This is a super layered problem, right? This is like the beautiful chocolate chunk cake with chocolate mousse, chocolate on top, right? You just start saying chocolate at a point because you don't know what else to call it because it has so many layers. Alright, so let's go ahead and start working on these examples. So this is going to be my first equation, and this is going to be my second equation. That's how I'm going to label these and work on them. So, equation number 1. So, first off, now there's a few different ways you can go about this. I guess you can start, if you really want to. You always want to do part 1 first, right? You always want to do the first skill first. You always want to figure out what the quadratic looks like and then determine the inequality. But as far as determining what the quadratic looks like, I guess you can do that in a variety of ways. So, as we know, there's multiple ways to show a quadratic. If we don't like it in this form, we can convert it into our vertex form. We can convert it from this form, which is called translational, into our vertex form. Or we can keep it just like that. It's up to you. I'm going to go ahead and keep it the way it is. I actually prefer this form, and I think it's a little bit easier to read. So, when we're looking for the vertex, remember, we're looking for what's going to zero out our parentheses. In this case, what zeroes out our y parenthesis is a -7. Okay? So, we're going to put -7 for our y value because -7 zeroes out this y term. Now, we're going to be looking for what zeroes out our x term, because remember, when we have both of these terms at 0, that gets us to our vertex. So, what's going to zero this term out will be when x equals 5. Right? 5 minus 5 is 0. So that's our vertex. Now what about our concavity? So remember, for concavity we're going to be looking for a negative multiplier. That negative multiplier is going to give us the opposite of our natural concavity. Natural concavity is up. Our equation naturally opens up and faces upwards, concave up. But if we have a negative on there, it's going to do the opposite, right? Negatives are opposite, so if we are naturally concave up, if we have a negative, we're going to be concave down. Alright? So, we're going to look for our negatives, right? Our negative multiplier. So I see a negative multiplier there, and I see a negative multiplier here. So I have 2 negative multipliers, and let's go ahead and conceptually think about this. What's the negative of a negative? Right? What's a double negative? It's just a positive. So these are actually going to cancel, and I can think of my concavity as being upwards, right? Because I have 2 negatives there. And side note, if I know it's up, I know that's going to imply a minimum. Right? Not required, but always good to know, good to get in the habit of. Now we're going to look for our stretch / compression. Okay? Now, I can go ahead and logically reason through this and tell you that it's going to be a compression. Right? How can I do that? Well, I can see that I need 6 of my y's to equal 2 of my x's. Right? 6 y's to equal 2 x's. Think about that. If you need 100 z-bucks to equal 1 calculator, what's worth more, the 1 calculator or 1 z-buck? Okay, so if I need 6 of my y's to equal 2 of my x's, that tells me that my x's are going to be worth more. So if my x's are worth more, I'm traveling more on my x, I have more of my x's for each of my y's, that means the graph's going to be going more this way. Right? It's going to be stretched horizontally or compressed vertically. Sorry, that was kind of weird the way I did that, but compressed vertically or stretched horizontally. Okay, because we're going more on the x's, our x's are bigger. Now, sometimes, so that reasoning takes a little bit more time. It's definitely solid reasoning. It's a great skill to practice, but it takes a little bit more time, and it's not always the most direct, right? And it doesn't necessarily tell us what our multiplier is, right? What the compression or what the stretch is. So let's go ahead and take a look at how we can move this multiplier to one side and then just kind of read it off. So the best way to do this is to move all of our multipliers to our x side. Now the reason for this is because this is simply what we're used to. We're used to having multipliers on the x side, not the y side. We're used to seeing our y's isolated and then all of the rest of our math on the x side of our equation. So let's go ahead, and down here I'm going to show my work for it. So I have just rewriting the equation right now. I have this equation, and I want to move all my multipliers to one side, specifically my x side. So how I'm going to do that is I want to get rid of this multiplier. I have a -6 multiplier, so how do I get rid of a -6 multiplier? I divide by -6. Right, just like that, those 6's are going to cancel, leave me with y plus 7. And what's going to happen? Right, up next I'm going to write the inequality. What's going to happen to the inequality? We cannot forget we're also dealing with inequalities in this, so we need to keep all of our same rules from our inequalities. Our rule from our inequalities is that whenever we divide by a negative, our inequality is going to flip. Okay, can't forget about that rule. So now -2 divided by -6, that's going to simplify to a positive 1/3. And then times x quantity x minus 5 squared. Cool. Okay, and this is cool. This affirms our concavity up here, right? We predicted a concave up. We see a positive multiplier here, right? Both negatives were gotten rid of. So it is concave up, which is good. That verifies that. Now, once our multipliers on our x, we can think about this in normal terms, right? Or I guess intuitive terms. That's a better way to put it. So if we have a 1/3 multiplier, is the number getting bigger or smaller? Right? Our number is getting smaller, so this is going to mean it's a compression. And it's a compression of 1/3. Okay, and by default, when we talk about these compression or stretches, it's in the y direction. It's in the vertical direction. Okay, and that's just because this is what we're used to. This is the way we normally do maths, the way we normally write it, the way we normally notate it. All right. So that is all of that. Now let's go ahead and put this on the graph. Okay, so I have all my key points: the vertex, the compression, the concavity, and the stretch and compression. Let's go ahead and put this on here. So my vertex is over 5, down -7. So 1, 2, 3, 4, 5, and then down 1, 2, 3, 4, 5, 6, 7. Down right there. Okay, it's concave up, and it has a compression of 1/3. Okay, so I know it's going to be opening upwards, but it's going to be doing so at a rate of 1/3 the normal quadratic. Okay, so side note, our normal quadratic goes like this. Right, I'm just drawing a graph of what our typical quadratic y equals x squared looks like. Okay, and the first point is 0, 0, and then the next one are 1, 1, and -1, 1. Right, back 1, up 1. Those are our next 2 points typically. So we're going to use that to predict where the other 2 points from this vertex would be. So normally they would be right there and there. Right, it's concave up, so it's still going to face up. Normally they would be right there and there. However, we have a compression of 1/3. So instead of going up by 1, we're going to go up by 1/3 of that. Right, so over 1 and then up 1/3, just up the tiniest bit. Okay? So something kind of like this. And then I can draw my graph. Okay? Just like that. Okay, so my quadratic is graphed. I just did part 1 of that skill. Let me go ahead and look at now part 2 of the skill, the inequality part of it. So I'm going to be looking to see if my inequality is equal to or not equal to. So I look at the sign, right? There's no line under here, which means it cannot actually equal it. It can get really, really close to it, but it can't quite equal this. So now this is why I always encourage you guys to do math in pencil, because if I were doing so, I could go back and just erase parts of it to make that dashed line nice and pretty. I don't have that option, so I'm just going to be emboldening parts of it to try and give it a dashed looking effect. I'm an artist. I embolden parts of my line to give it a dashed effect, to further convey the idea of inequalities to my aspiring students. That's my artist statement that I'm speaking right now. Okay, so I hope that has a dashed looking effect to it. That's not bad. That works. Okay, so it's a dashed line, can't quite be equal to it, can get close to it, but can't get onto it. And then, now my y or x, which one is bigger? Okay, and you always want to look at this version. You don't want to look at it with multipliers on the y. You want to look at it once your multipliers are on the x. So it's actually really convenient to get it into this form, because now it's easier to read off for both parts of our inequality. So right now we can tell that y has the bigger side of our inequality, right? It's opening up towards us, which means our y is bigger. Our y is bigger. This means we're going to be shading up. So shading everything above this inequality, just like that. Okay? Cool. First inequality done, and we're already past 15 minutes. Yeah. Part 2. I know this is a big one. But right, this is a full body workout. This is a full mind workout, right? Think about all the practice you're getting in with just one problem, right? It's excellent. So let's go ahead and look at number 2. So number 2, this is a little bit easy to read in terms of part 1, in terms of looking, graphing finding our key features, just because it's in vertex form, so it's a little bit easier to read that stretch or compression. So let's go ahead and do our vertex. Now we're going to look for what's going to zero out inside the parentheses. So right, what's going to zero this out would be 3. So our vertex would be 3. And now what about our y value? We notice it's not in parentheses. So if you want, you could actually subtract over 6 to this side to put it into parentheses, right? So you would have negative 6 minus y. And then you would realize that, oh hey, that a negative 6 would cancel this out, right? Negative 6 minus negative 6, that would bring it to 0. Or you can just go ahead and look at the sign over here. Okay? But one quick caveat to this. We see a negative multiplier on the y, so you may be tempted to say that the vertex is positive 6. But we actually have to remember that this is the negative y. Right? I guess the easiest way to see this might be to skip ahead to moving the negative over to the other side. Okay, so algebraically, if we go ahead and we move this negative over to the other side, right, so we divide both sides by a negative 1 to get rid of that negative there, right? That's like implying a negative 1 multiplication, so we divide by negative 1. That's going to cancel that out, so we'll have y. Our inequality, what's it going to do? We divide it by a negative, it's going to flip. And then 2 divided by negative 1 is negative 2 parentheses x minus 3 squared. And then, don't forget, we also have to divide the plus 6 by the negative. 6 divided by negative 1 is negative 6. Okay, so our vertex is actually negative 6. Right? The y value for our vertex is actually negative 6. Now you could see that if you went and you brought it over to there, you could then say, okay, what's going to zero out my y? I know that negative 6 will zero this out, right? Negative 6 minus something. Well, it's got to be minus the same thing, so just negative 6. Or you can convert it to vertex form and then find it. Right, remember, 2 ways of doing it. I want you to do whatever is easiest for you, do whatever is the most reliable. Cool. Our concavity, right? What is our concavity? So we're going to look for that negative multiplier. We see our negative multiplier right there. So that's going to mean that it's going concave down. Normally it's concave up, but if we have a negative multiplier, we do the opposite, which is concave down. And I know that concave down means we have a maximum. Hi, Max. That's Max. Awkward shoutouts. I would apologize, but I'm really not sorry. Okay, stretch and compression. Okay, now the stretch on this, or the compression, how am I going to tell? I'm going to look for what the multiplier, I'm going to look at the multiplier. Now remember, if all my multipliers are on my x, I can think about this intuitively, right? I see a multiplier that's bigger than 1, right? 2 is bigger than 1, so anything it multiplies is going to get bigger. So therefore, it's going to be a stretch of 2, right? I'm going to have a stretch of 2. And another way to think about that is that I need more x's to get to my y's. So my y is going to be bigger, so I'm traveling more on my y-axis than my x-axis. So it's pulled that way. Okay? So, nice. I got all the stuff that I need to graph this thing, to graph this bad boy. So let's go ahead and do it. So let's start off with the vertex. We're going to go over 3. 1, 2, 3. Then we're going to go down 6. 1, 2, 3, 4, 5, and 6. This is going to be a weird one. This is going to be a weirdo. That's what my parents said when they first saw me. I don't know. So, right, this one's going to be down to right here. And we're going to have a stretch of 2. And it's going to be concave down. Right, so it's concave down, it goes like this. It's going to be open downwards, stretch of 2. So instead of looking like this, right, instead of having that typical over 1, up 1, back 1, up 1, we're going to be going back 1, down 1, and over 1, down 1, and we have a multiplier of 2. So that means instead of going down by 1, we're going to go down by twice that. So we're going to go left 1, down 2, and then right 1, down 2. Just like that. So our quadratic is going to look something like this. Now, notice, right, they're getting really close. They may or may not have overlap. And if they don't, that's okay, but just we're gonna think about this once we shade it in. Let's first go ahead and look at this a little bit further. So we draw that. Is it supposed to be a solid or dotted line? Solid line, right? It has that or equal sign. And is it going to be less than or greater than? Right? It's going to be less than. Y is less than our x term, so that means we are shading below it. Okay? Now, the thing is, from the sketch I drew, we would actually have to get a little bit more detailed to see if they actually intersect. And if they do intersect, right, say that maybe they intersect right over here, there's just a little tiny bit that's shared and shaded, that would be my solution set. My solution set is wherever these two regions overlap. Right? So now the natural question, what if they don't overlap? Well, that's okay. That just means we have no solutions. Right? Mr. Zoyas gave us a problem with no solutions. Why would you do that? You mess with my head. I'm learning new stuff and you give me a no solution problem? I know, right? Always throwing curveballs at you, but I promise it will make you stronger. Okay? So, understand, if they don't overlap, that's okay. It just means it's no solution. But where they do overlap, that's where our solutions lie. Okay? And so, that is both of these graphed just like that.